Now, the last part of this chapter is a mix of this chapter and the previous one. In the previous chapter, we learned about the binomial distribution, and we saw how to do that. We saw how to find the probabilities. Now, if you have a situation where it's a binomial question, but you have a really large sample size, then taking the binomial route would take forever. Because remember that with binomials, you have to find the probability of every outcome that satisfies your question. And when it's 3-4 outcomes, that's okay. You can do it by hand, manually. But when it's hundreds of outcomes, it would take you forever. And so what we're able to do is you could approximate the binomial probability using a normal distribution as long as the sample size is large enough. Now, what is large enough? You have the rule right here. As long as NP, this is binomials now, right? As long as NP, which was the expected value, is more than 5, at least 5, and then N times 1 minus P, or N times Q, is also at least 5, then you can approximate the binomial using the continuous probability distribution, and that's what I want to show you guys here. Essentially what you're looking at, the black line is the bell curve, the normal distribution, and the blue bars, those are your binomial outcomes. So before we get into how to do it, the first thing you need to understand is how can you express something that is discrete, meaning can only take a whole number. How can you express it using something that's continuous? Like if I ask you how many classes you're taking, you can take 2 classes, you can take 3 classes, but you can't take 2.4. So then how would I say that, but using a continuous distribution? I'm going to show you using this bell curve. Now let's pick any number. Let's pick the number 10. 10 is 10, right? You have 10 friends. You have 11 friends. You have 12 friends. You can't have 10.3. But how do I express the number 10 using something continuous? Well, the number 10 is everything between 9.5 and 10.5. 9.5 and 10.5. So asking you the probability of 10, right, as a binomial becomes asking you the probability that x is between 10.5 and 9.5 using the continuous probability distribution. That's called a continuity correction. And it seems weird at first, I get it, but that's how you do it. You always want to use 0.5 basically, right? The number 10 is everything from 9.5 to 10.5. So we're going to do a few exercises so you understand how to do it. And then this chapter will be done. So in a study, 350 randomly selected students, so that's my sample size, asked if they support a new policy regarding campus safety. Out of the 350 students, 220 said they support the new policy. Suppose that before the survey was conducted, a student organization claimed that at least 70% of all college students would support the new policy. Okay, so there's your P. 70% of all college students would support the new policy, right? That's P. Calculate the probability that 220 or fewer of the 350 randomly selected college students would support the policy. Now, this is a binomial question. I never talked about normal distributions. It has all the characteristics. There's a repetition, there's a probability, there's only 2 possible outcomes, either they support it or they don't, and every student is independent. But the sample size is so big, right? So if we did n times p, if I took 350 times 0.7, that's 245. And then if I did n times 1 minus p, so 350 times 0.3, that's 105. Both of these are at least 5, which means I'm able to answer this binomial question using a normal distribution instead. So let me show you how to do that. You need 2 things, first of all. You need the mean, which now we know, we learned in the previous chapter is n times p. We actually have that written up there at the top. And you need the standard deviation, which is the square root of npq. Again, this is from the binomial chapter, guys. So let's do the math on this. Your standard deviation is 8.57. Great. Now the question is, now if I were to draw the bell curve, now we're going to convert this to a continuous probability. So the mean is 245. That's here. They're saying that calculate the probability that 220 or fewer, so 220 would be here, or less. So we're looking for the area to the left of 220. Now, here's where you have to use your continuity correction. Because we want the area to the left of 220, the probability that x is less than or equal to 220, because they said 220 or fewer, we need 220 to be included in the sample, in the outcome. Now, with the continuity, remember that 220, technically, if we do the continuity correction, is everything from 219.5 to 220.5. 0.5 above and 0.5 below, right? Let that sink in for a second. We said before that any single number is actually a range, 0.5 above, 0.5 below. So if you want to include the 220, you basically are saying, I need everything that is less than or equal to 220.5. Because 220 is not 220. 220 is from 219 to 220.5. Now, if you're wondering, well, why didn't I use 219.5? Why did I go to the upper side? Well, it's because I'm looking for everything below it, right? So the 219.5 is included in this. So if you're looking for the area to the left, but you want to include the number, you need to include the whole number. If you would have done this, if you would have said, okay, continuity correction, less than 220 means less than 219.5, then you've technically excluded the 220 because you're saying everything that is 219.5 and below. The 220, which is the range of this to this, is not included in that. So if you want to include 220, you go to 220.5. If you didn't want to include it, like let's say the question had been less than 220. Let's say the question was actually less than 220, then it would have been this. Because here you would actually be trying to exclude it. That's the continuity correction. And from this point, it just becomes a regular z-score question. So we're actually looking for 220.5. So I'm going to find my z-score using 220.5 instead of 220. X minus mu over the standard deviation, just like we've been doing this entire chapter. So 220.5 minus 245 divided by 8.57 is negative 2.86. Negative 2.86. We go look that up in the table. Negative 2.8 and 6. 0.0021. That's our answer. So we want the area to the left. So that's it. That's the area to the left. Let's do another one just to be sure. Calculate the probability of exactly 260. Okay, what is exactly 260? Exactly 260, we said before, is everything that is between 260.5 and 259.5. And that's how we're going to solve it. You've got your bell curve with a mean of 245. And I'm saying, tell me the area between 259.5 and 260.5, which corresponds to the value 60. And then you're going to do it the same way we learned earlier in this chapter. If you're looking for an area in between, we'll start by doing the z-score for both. So 259.5 minus 245 over 8.57. And then 260.5 minus 245 over 857. For this one, I get 1.69. 260.5 minus 245 divided by 8. And then here we get 1.81. So let's go look both of those up. 1.69 is 0.9545. 0.9545, and then 1.81, 0.9649. The area in between is the difference. So 0.9649 minus 0.9545, basically 1%, 0.0101. One more. Calculate the probability that more than 260, probability of more than 260. Is the 260 included in that? It's not, right? Which means I want no part of it to be included. 260 is, again, everything from 259.5 to 260.5. So I want no part of 260 to be included. So this, after we do the continuity correction, we want everything that is above 260.5. If I don't want the 260 included, I don't want any part of it included. So I'm going to go everything above 260.5, and that's it. That's your x. So you'll find, so if I draw my bell curve, I get 245 is my mean. I'm looking for everything above 260.5. Oops. And we already have this because we just did the answer above. We know that if we look up 260.5, we have a z-score of 1.81, which is an area of 0.9649, but I want the area to the right of that. So 0.0351. That's my answer.